Hi, this screencast is about properties of light and some terms that are associated with waves. So some terms you need to be familiar with are wavelength and frequency. Wavelength is shown with the symbol lambda, which is right here, and that is the distance between corresponding points on adjacent waves. So if we look at our diagram from crest to crest, that is the wavelength. Frequency, or the Greek letter mu, is defined as the number of waves that pass a given point in a specific time, usually 1 second. So if I was standing right here and I was counting how many of these waves pass in 1 second, that would be the frequency. This diagram also shows some other variables that you need to know. One is the amplitude. Amplitude is the distance from the midline to the bottom of the trough, or from the midline up to the top of the crest of the wave. And the speed of light, which is something we're going to talk about here in just a minute. So make sure you're familiar with these terms: wavelength, frequency, amplitude, and so forth. Frequency and wavelength are proportional. So when we have a high frequency, we have a short wavelength. And you can see here, because if I was standing right here at this point, several of these waves would be passing me in 1 second, as compared to this wave, which is low frequency and has a longer wavelength. So I would get fewer waves passing me at this point per second than I would at this point. So if we have high frequency, it's going to be a short wave. Low frequency will be a long wave. Frequency and wavelength are mathematically related to each other with this equation. C is the speed of light equals lambda mu. In the equation, the speed of light is in meters per second. Lambda is the wavelength of the electromagnetic wave that's in meters, and mu is the frequency of the electromagnetic wave. That's in seconds to the -1 power, which is 1 over seconds, or hertz, which is the unit that we use to denote frequency. So the speed of light is shown here, and it's in meters per second, but we round it to an acceptable value of 3 × 10⁸ meters per second. But in a lot of our problems, we're going to be using centimeters per second or nanometers per second. So that means we need to convert. So some conversion factors to help you: 1 meter equals 100 centimeters. 1 meter equals 1 × 10⁹ nanometers. You probably want to make a note of these in your notes because we'll be using them throughout this chapter. Let's look at how we solve a problem. A sample of light has a wavelength of 3.4 × 10⁹ meters. What is the frequency? We're going to start out by taking a look at our equation. The speed of light is equal to frequency times wavelength. So we have 3.0 × 10⁸ meters per second. That's our speed of light. Our wavelength is 3.4 × 10⁹ meters, and we're looking for frequency. In order to get frequency by itself, we're going to have to divide both sides by the 3.4 × 10⁹ meters. So when we do that, we're going to take 3.0 × 10⁸ meters per second divided by 3.4 × 10⁹ meters, and we get 8.8 × 10⁻XVI seconds to the -1 power. We will be doing several of these problems in class, so make sure you write this sample problem down in your notes, and you refer back to it as we're solving problems on properties of light, and the equation for the speed of light is the frequency times the wavelength. Write any questions down and make sure you ask Mrs. Benke in class if you don't understand anything.